Okay, mass energy calculations. There's two types that we're going to be dealing with. One is where we're going to deal with the mass, the change in mass and energy for a radioactive decay, and the other is where we're going to talk about the mass defect or binding energy of an atom. So for the radioactive decay here, it could also be a bombardment reaction as well, but we'll just stick with this. What you do is you'll have a table of masses. You can see how many significant figures we want to keep, because the change in mass often is very slight, so even though the change in energy will be gigantic, we need to go to find the change in mass. We need to carry out a lot of significant figures. So they want to know the energy change in joules, and then also from mega electron volts next. So what we do is you take the masses of the one side, add those up, subtract off the mass of the other side of the reactant side, or the starting side, and that gives us a change of 0.01158 AMU. And if it comes up negative, I mean, that's what it should do. There should be a loss of mass, but I don't worry about that. That's just telling us how much mass is gone. So that's our loss of mass, our change in or change in M, or change in mass. And this is also, it's AMU, so it's also grams per mole. So what I do is I just deal with AMUs and then I change over to grams per mole. Now, and then we change this number to kilograms and put it in directly into the E equals mc squared. So we're not interested just in energy equals mass times the speed of light squared. We're interested in the change. That's what is going to be important for us. So we take the change in mass times the speed of light squared, and you end up with 1.04 times 10 to the 12th joules per mole. That's a trillion joules. That's massive. Now, because that's so astoundingly large, it's hard to get a grasp of it. So what we'd like to do is convert it into a unit measure that gets us somewhere between 1 and 100, and that's what mega electron volts do. So you take this, convert to joules per nuclei. So mega electron volts and electron volts are about the change in energy of one nucleus. So we change back to joules per nuclei, and then for every joule of 1.602 times 10 to the minus 19 joules, that's 1 electron volt, and then 10 to the 6th electron volts is 1 mega electron volt. So an electron volt is the energy that one electron picks up in traveling through 1 volt, a 1 volt potential. So this is 10.8 mega electron volts. It's pretty massive. So gives you an idea. This one gives you an idea of the energy just from your own. So this is 10 to the 9th kilojoules per mole. Most of our chemical reactions are less than 10 to the 3rd. So this is a kilojoules per mole. So this is, say, 1 billion times or 10 billion times higher in energy for this process. So whatever reaction I give you, add up the product masses, reactant masses, subtract them. Whether or not they're positive or, I mean, it should be negative, but just take that mass, change to grams per mole to get grams per joules per mole, and then use this equation to go to mega electron volts. Now you can go directly from here to mega electron volts, but this is a nice standard way of doing it, something that you can do each time, and that's the way I prefer to show it. Now, determine the binding energy and mass defect of iron 56. Okay, so in your textbook there's a table that gives you the mass of the iron 56 atom. And that's 55.93494 AMUs, or grams per mole. So what I do is we'll look at what we want to do is see what is the mass of the total, or what's the mass of the protons, neutrons, and electrons in total, and then what's the mass of the iron atom when they're put together. So we take the mass of the particles, the building blocks, before we put them together, then afterwards. And whatever the mass difference is is related to the binding energy, and that shows you why they stick together. So we're just going to find the mass of each of these particles: 26 protons, 26 electrons, 30 neutrons. And I did it per grams per mole. They do it by AMU, but since we're going to have to convert to mass anyway, kilograms when we put it into this equation, I just decided to change it over here. But you could, this is grams per mole. We could certainly do it by AMU. So you just add them all up: 26 times the mass of a mole of protons, 26 times the mass of a mole of electrons, and then neutrons, and we get this, and this is really per mole. Now, the iron 56 atom is 55.93494 AMUs, or this many grams per mole. So if we, for 1 mole of this substance, we subtract the two, and we find that the difference would be 0.528564 grams for the mass defect. Convert that to kilograms, multiply by the speed of light squared, and we end up with this, which is the binding energy. That mass that disappeared, or seemed to disappear, went into, that was released, that energy was released. That's what's holding the iron atom together. And I chose the iron 56 atom because that is really the most stable isotope that there is as far as we're aware of. So you can see this is pretty massive. And then changed it over to mega electron volts. 494, that's extremely large. So for whatever isotope that I give you, or what, you should be able to just take it apart into protons, electrons, and neutrons, add up their masses. The mass of the isotope must be in the table so that you can subtract them, and you solve it in that form.